Hello class, welcome to today's lesson, which is 5.2, and we're gonna discuss the derivative of polynomial functions. So remember, what were polynomial functions? A polynomial function is a function that looks like this. For example, f of x equals 4x to the 3 minus 2x to the 2 plus 5x plus 3. That's a polynomial function. Another example, g of x equals 8, x to the 7 minus 7x to the 4 plus 3x squared minus 1 half, okay? And I could go on and give you many examples, but let's stop right there. So a polynomial function is a function that looks like this, okay? And the basic properties that you must understand is that a polynomial function is a function in x such that the exponents in the x are always positive integers. Okay? Positive integers. I repeat, positive integers. Something like this, g of x equals 5x to the minus 2. This is not a polynomial function. Okay, so it's you know, they look like very well-behaved functions, so to speak. They look nice. So that's a polynomial function. And we want to find out a way to get the derivative of this type of functions very quickly, okay, without the use of the basic formula that we have already discovered, which is that the derivative of a function f prime of x, that is the derivative, is given by taking the limit as h goes to 0 of the quotient f of x plus h minus f of x over h. That is perfectly okay, and you can find the derivative of most functions with this one. Why do I say most functions? Because sometimes uh, doing it with this, even though this is the definition, getting easily the derivative of a function which is complex may not be as easy, okay? And you may not be able to do it algebraically, but those are rare functions, and we're not gonna look at them. So this is our base formula, but it's too long, right? Working out with this formula, it's way too long. So how can we get derivative of functions in a much simpler way? Okay, so let's start the analysis. Remember, what we want to do is get the derivative of functions that look like this, polynomial functions. Okay, we're gonna start in very simple terms. Let's remember something. Let's remember that we have already done the work for this function. We have already gotten the derivative, okay? If my function is f of x equals x squared, then the derivative of f is given by 2x. And you actually did this process, okay? So you must understand how this works. You did the whole process of the limit and the formula and blah, blah, blah. Okay, so we got this down. Now, what if we go one level above? What if we try to calculate the derivative of this function? F of x equals x to the q. What do you think the derivative will be? F prime of x, what's gonna be in here? Okay, let's discover that very quickly. Let's do it by the long road. F prime of x, and I'm talking specifically about this function f. They are called the same way, but I'm referring specifically to this function f. The derivative is going to be given by the limit as h goes to 0 of the quotient this one, right? And that's it. And all I need to do now is go along with the process. F prime of x, or the derivative of f at x, is going to be equal to, I'm going to write this long L in order to represent all of these symbols, okay? So this long L represents the limit as h goes to 0 of f of x plus h, and that's going to be x plus h to the cube, because now my function is x to the cube, minus f of x, which is x to the cube, over h, then the derivative of the function is equal to the limit as h goes to 0 of all of this. This is a binomial to the cube. I hope you remember how to raise it very quickly. It's going to be this. It's one of those things that it's a good idea to have memorized. Okay? If you don't trust me that this binomial to the cube is all of this, you can do it on your own in a moment or later. Let's continue over here. So now we have that f prime of x is equal to the limit as h goes to 0 of what? Okay, let's see. X to the cube, we have x to the cube here and minus x to the cube. So I know that I can cancel these two terms right away. And I'm only going to be left with the following. 3x squared times h plus 3x h squared plus h to the cube over h. And now, if you remember well, the key process in all of this is the division over 0, right? Dividing each of these terms, this, and this, over h. Why can we do that? Because h, even though it's approaching 0, is not 0. That's why I can get away with doing this, dividing this over this over this, and this over this. So let's do it. 3x squared times h over h. I'm going to get simply 3x squared, right? And then 3x squared over h. I'm going to get 3xh, right? And finally, h to the cube over h. I'm going to get h squared. We close the brackets. And now for the final step. Remember, what does this symbol mean? It's the limit as h goes to 0 of whatever I have inside. And finally, we just take the limit. Remember, if there is no, if you evaluate the limit, in this case in 0, and nothing weird happens, like divisions over 0 or things like that, you can do it just fine, no problem. So basically, the limit as h goes to 0 of this whole function is basically the evaluation of this function in h equals 0. So basically, it's putting a 0 right there and a 0 right here. And as you can see, by doing so, this term will go to 0, this term will go to 0, and the final answer that we will get is that f prime of x is going to be simply this term. This is the only term that's going to remain alive, so to speak. And we are done. Okay? If my function f is equal to x to the cube, then we have proven that its derivative, f prime of x, will be equal to 3x to the square, according to this result. Okay, perfect. As you can see, this takes us a lot of time. Well, in my opinion, this is a lot of time. It's not fun to do this every time we want to calculate a derivative. This is a time-consuming process. You may make mistakes, etc. Okay, so it's not, mathematicians are often lazy people, and what we try to do is try to get things done quicker, okay, by using our brains. That's why you have your brain, so that you don't waste time doing stuff like this. If you can find a better way to do stuff, find it. That's what the brain is for. Okay, now I'm going to give you just other two examples. If I had this function f of x equals x to the 4, then if I did the same process that I did a moment ago, which I'm not going to repeat for time reasons, you will get that the derivative will be 4x to the cube. Okay, you can trust me on this. If this is the function, this is its derivative. Now, if this was the function x to the 5, then the derivative will be 5 times x to the 4. Okay, and so on. If you get f of x equals x to the 6, then its derivative will be f prime of x equals 6x to the 5. So what is the pattern that is appearing right there? Okay, look at all these results, and what is the pattern that is coming up? It's very clear, right? What is happening is that if we have a function of this type, x to the something, when that something is an integer, then its derivative is that exponent. You see, in this case, the exponent is 3, x to the 3, and its derivative will be 3, the exponent that we had before, times x raised to 1 less than the exponent before. You see, 3 minus 1 is 2. Now, in this case, my function is x to the 4, and its derivative will be such exponent as we had before, you see, times x raised to 1 less than the exponent we had before. 4 minus 1 is 3. And the same for the other two. Can you see the pattern? Okay, so this, you cannot conclude that this pattern will be true for all eternity, for all the cases, okay? In mathematics, when you observe a pattern like this, that doesn't mean it's true. It means that it's possibly true, and now all you have to do is prove the general result, okay? What would be the general result? If you want to generalize this result, you would have to say, okay, I get the idea. If I have f to the x being equal to x raised to some integer, positive integer, I repeat, guys, positive integer, okay? Then this pattern tells me that f prime of x should be equal to such exponent as before, which is n, times x raised to n minus 1. You see? I'm just following the same pattern. Now, is this true? Maybe, maybe not. We have to prove it. And I'm going to give you the answer right away. Yes, it is true. Okay, it's going to be true, and we're going to demonstrate that. Okay, in order to demonstrate such general result, I need you to remember about the binomial raised to an exponent, okay, or the binomial expansion, or the binomial theorem, right? For example, x plus y to the square, that one is very simple, right? We know it by heart. It looks like this, and we can raise the same binomial to either the cube, the fourth, the fifth power, the sixth, whatever, and we get these types of expansions. Okay, what do I want you to look at or to understand? Well, first, you're going to have as many terms as the exponent plus 1. If the exponent is 3, you're going to have 4 terms. 1, 2, 3, 4. If the exponent is 4, you're going to have 5 terms. 1, 2, 3, 4, 5, and the rest is similar. What else can we see in here? If you look at all the terms, you can notice that the exponents in the x go downwards by 1. X to the cube, x to the second power, x to the 1, and x to the 0. And we always begin with the power, which is the same as the exponent in the binomial, okay? X plus y to the 3, and then we're going to begin with x to the 3. Same here, 4, 4, 5, 5, etc. Okay, so the exponents in the x go downwards, the exponents in the y go upwards. This is y to the 0, or basically no y. This is y to the 1, you see, y to the 2, y to the 3. The same for the rest of them. And the other thing that I want you to notice is that is these coefficients, okay? 3, 3, 4, 6, 4, 5, 10, all these coefficients in the middle. The first coefficients are always 1, and the last coefficients in here, in this one, this one, this one, this one, and this one, is always 1, 2. Okay, so these coefficients are not important in general. Only the only important one for us will be this one, the first coefficient different than 1. In this case, this coefficient, which is 3, this coefficient, which is 4, 5, 6, and 7. What is the pattern here? That it's also going to be the same as the exponent in the expansion, okay? If the exponent is 3, then the first coefficient different than 1 will be 3. If the exponent is 4, the first coefficient different than 1 is 4, and so on. That's all I want you to remember, okay? Okay, because we're gonna use these results or these facts or these features of the binomial expansion in a moment. So let's go to our demonstration. What do we want to prove? I want to prove that if f of x is equal to x raised to a positive integer n, and I'm gonna make that precise statement, n being part of the natural numbers, then its derivative, f prime of x, is going to be equal to such exponent n times x raised to the n minus 1. Okay, this is the theorem that I want to prove. This is a theorem, a statement, and I want to prove it. So the demonstration is as follows. Pay attention, because I'm going to ask you to demonstrate it once again, like you did the other demonstration of the formula for the derivative. Okay, so let's start. How do I start? Well, I write the basic formula for the derivative, which is the limit as h goes to 0 of my quotient f of x plus h minus f of x over h. Okay, and I continue reasoning from here. So f prime of x is going to be equal to the limit as h goes to 0. This is not a standard symbol, okay? I just made this up. Do not think that this is the same as this in mathematics. This is just my notation. Okay, f of x plus h. If f of x is equal to x to the n, then f of x plus h will be x plus h to the n minus f of x. How much is f of x? It's x to the n over h. Let's continue. F prime of x is going to be equal to the limit as h goes to 0 of the following. Let's expand this binomial to the n. Okay, now it's difficult because it's an unknown exponent, right? So what we can do is just this. What's going to be the first term? The first term is going to be x to the n, like we said before. That's going to be your first term. Then we're gonna have plus a coefficient different than 1, which is the same n as the exponent, times x to the n minus 1, because remember that the exponents in the x variable go downwards by 1, and then the first h appears right here, which is this variable. Okay, this is the second term. Then comes the third term, which one coefficient, which for the moment I don't care what this number is, so I'm just going to call it C1. It's just some coefficient. We don't care what it is. Times x to the n minus 2, because we go 1 downwards from this one, times h to the square, because the exponent in the h goes upwards. Okay, and so we have the same pattern until we eventually get to another coefficient, x to the 2 times h to the n minus 2 plus another coefficient times x to the 1 times h to the n minus 1 plus, I made a mistake here, this is C3, this is my coefficient number 3, plus another coefficient. Well, no, this one doesn't have a coefficient. The last term in this expansion will be h to the n, and all of this is being divided over h. It's a very long numerator. Okay, so it's gonna look like that. Okay, remember the C's stand for coefficients. What coefficients? We don't care. It's not important. It's not important at all. Okay. Oh, by the way, I also forgot something. All of this, all of this numerator so far is just the expansion of x plus h to the n. But we already have this one, right? So I was forgetting about that. Minus x to the n. So I'm going to include it here. Minus x to the n. We close the line and close the brackets. Okay. So this looks like something very complicated, right? Okay. So let's continue. F prime to the x will be equal to the limit as h goes to 0 of what? Okay, same idea. We look at this x to the n and we observe that we have another x to the n but negative. So we can cancel this one and this one. And the other thing I can notice is that I have this term which I can divide over h, this other term which I can divide over h, this other term which I can divide over h, and so on. I can divide each of these terms and all of those in here, okay, in between, over h. So let's do it. This term over h will be this. Do you agree? Because it only has one h and one h in here. So the h's disappear. Now this term, all of this term over h, what are you going to get? You're going to get the following, right? Because you have h squared over h, you're going to get h plus etc. Now this is the term. When you divide this over h, you're going to get c2 times x to the 2 times h to the n minus 3. Okay, properties of the exponents. H to the n minus 2 over h is going to be equal to this. Plus, I'm going to complete it now on my own. This is what we're going to get. Okay, so this is what we're going to get in the end. After we divide all these terms in the numerator by h, we're going to get all of this. And finally, we do the same trick as before. Let's now take the limit. Remember that this symbol, what it means is the limit as h goes to 0 of all of this stuff. And if you notice, what's going to happen? Well, this term, all the terms in here in between, which are not appearing because it's impossible to write all of them, this term, and this term all contain h, all of them, except this one, you see? So when we evaluate this limit in h equals 0, basically this term is going to go to 0 because you have h in here. So whatever times 0 is going to be 0. Whatever times 0 is going to be 0. All of these terms are going to be 0 because of the same fact. And everything is going to disappear except this term. This is the only term that is going to remain alive. And we can conclude, therefore, that f prime of x will be equal to n times x raised to the n minus 1. This is the result that I expected, right? This is what I wanted to prove, as you can see in here. If my function is x to the n, then its derivative is n times x to the n minus 1, as long as n is a natural number or a positive integer. So we have proven the result, guys. So how can I put this new result into use? Well, let's look at some examples. I think 3 will be enough. If I give you the function f of x equals x to the 10, if I give you the function g of x equals x to the 7, and if I give you the function h of x equals x to the minus 2. Let's see if we can get the derivatives. Okay, so in this case, I just apply the formula. The derivative of f, which is this, is going to be simply the exponent that we had before, which was 10. So this exponent is like dropped down, so to speak. Okay, it becomes a coefficient of the x, so to speak. So it's going to be 10 times x raised to the 9 because it's one less than the exponent before. Okay, and this is the result. This is the derivative of this function. Very simple. If g of x is another function and g is equal to x to the 7, then g prime of x, or the derivative of g, is equal to 7 times x to the 6, according to my result that we found a moment ago. Now, what about this? What if they give me h of x equals x to the minus 2, and they want me to calculate the derivative? Can this be done? Yes. Yes, we will be able to do this later. Can we do it at this point with my result? The result that we got already? No. Why not? Because my result is very clear in saying that the following, that this exponent has to be a positive integer, okay? Positive integer so far. So at this point, we cannot find the derivative of this function. It does have a derivative. We will be able to get it, but not at this point.